Hello, everyone, and welcome to today's webinar in the CERDP and ESTCP webinar series. My name is Rula Deeb. I'm a senior principal at Geosyntac in Oakland, California, and the coordinator of the webinar series on behalf of CERDP and ESTCP. I'll be facilitating today's call. This webinar will consist of a brief overview of the CERDP and ESTCP programs, followed by the technical portion of the webinar, which will detail results from Department of Defense funded research on modeling tools for vapor intrusion and cost-effective mitigation. First, Dr. Eric Suberg from Brown University will discuss the vapor intrusion processes responsible for large variations in indoor air contaminant concentrations identified through a combination of three-dimensional computational fluid dynamic modeling and statistical analyses of data sets with extensive temporal data. Eric's presentation will be followed by a Q&A session. Dr. Todd McAlery of Geosyntac will then discuss new tools to reduce the cost of mitigating volatile organic compounds and radon intrusion into buildings. His presentation will also be followed by a Q&A session, and we will conclude the webinar with another session featuring both of our speakers. On this slide, we have provided a few suggestions in case you experience difficulties with the broadcast platform. Firefox, IE, or Edge are the most compatible browsers to use. If you lose the content on your screen or if your screen freezes, try keying Control F5 to perform a hard refresh. If you are accessing the audio through your computer, click the arrow next to the Join Audio button, select Test Speaker and Microphone, and follow the prompts as they appear on your screen. If you continue to experience difficulties, please call into the conference line shown here. You may also submit a comment using the chat box. Please use that chat box only for comments related to technical difficulties. The Q&A option should be reserved for questions for the speakers. Today's broadcast will be listen only. You may submit questions by using the Q&A box on your screen. You do not need to wait until the Q&A period to submit your questions. In fact, we encourage you to submit questions well in advance of the Q&A session. When submitting your questions, please make sure to add your organization name at the end of your question so that we can identify you during these sessions. With that, I would like to introduce Dr. Robin Nisan, who is the CERDP and ESTCP Program Manager for Weapons Systems and Platforms. Before joining CERDP and ESTCP, Robin worked at Navarre's Weapons Division, China Lake in California. Robin?
Thank you, Rula. I'm pleased to welcome everyone to today's CERDP and ESTCP webinar. CERDP is the Strategic Environmental Research and Development Program. It was established in 1991 by Congress as a partnership between the DoD, the Department of Energy, and the EPA. CERDP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. CERDP funds both fundamental research as well as advanced technology development, which ultimately impacts real-world environmental management. ESTCP is the Environmental Security Technology Certification Program, in which we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under CERDP or other research programs that are designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. CERDP and ESTCP are complementary programs, with much of CERDP research occurring at the lab and pilot scale, with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts are conducted as well. There are 4 program areas in CERDP and 5 in ESTCP. The Installation, Energy, and Water program area is only in ESTCP, while the other 4, environmental restoration, munitions response, resource conservation and resiliency, and weapon systems and platforms are CERDP and ESTCP programs managed jointly by a designated program manager. Our webinar today is focusing on research and demonstrations that were conducted under the Environmental Restoration Program area. Environmental restoration has 5 main areas of research: contaminated groundwater, contaminants on DoD testing and training ranges, contaminated sediments, wastewater treatment, and risk assessment. Our webinar series highlights research and demonstration efforts from each of the 5 program areas. As you can see, upcoming webinars will cover a broad range of topics, including understanding underwater munitions mobility and behavior on the beach face and in shallow, muddy environments, building energy and water efficiency solutions, recovery of native plant communities on Pacific Islands, and tools for sustainment and health. The next ER webinar will be held on September 5th and will feature 2 speakers on the use of advanced molecular biological tools in groundwater contaminated with chlorinated solvents. You can find additional information about upcoming webinars at this link. Registration is now live for webinars through the end of this year. I would like to remind you that a copy of the presentation of today's session can be downloaded from our webinar page. We would appreciate it if you could please take a moment to complete the survey that will pop up on the screen at the end of the webcast. And I am very pleased to announce that the CERDP and ESTCP Symposium will be held again this coming December in Washington, D.C. at the Waterman Park Marriott. The 3-day event will showcase the latest technologies that enhance DoD's mission through improved environmental and energy performance. Registration information is now available on the CERDP and ESTCP website. I hope you'll enjoy today's webinar. Back to you, Rula.
Thanks, Robin. And it is now my pleasure to introduce our first speaker today, Dr. Eric Suberg, who serves as Project Leader, Research Translation Core Leader, and Associate Director of Brown's NIEHS-supported Superfund Research Program. Dr. Suberg was a co-founder of Brown's program in chemical engineering, as well as co-founder of the Master's Program in Innovative Management and Entrepreneurship. His research focuses on chemical thermodynamics, kinetics, and transport. His work in the Superfund Research Program and ESTCP program relates to vapor intrusion and combines study of the thermodynamics of interface partitioning with consideration of the vapor intrusion transport processes that bring contaminants to receptors. Dr. Suberg is a registered professional engineer in Rhode Island. Eric, please proceed.
Thank you, and let me add my welcome to those of the others. Let me start by saying that I've been involved with vapor intrusion research about 15 years, starting this work at the request of our partners in the Superfund Research Program at the Rhode Island Department of Environmental Management. From an objective of understanding vapor intrusion on a fundamental level, this quickly brought us to examine what engineering mathematical models can offer to understanding this complex set of phenomena. In terms of the presentation today, this is a brief outline. I'll cover the benefits to the Department of Defense first, but the main focus is going to be on understanding the vexing problem of transients in vapor intrusion that makes life so hard for regulators and environmental professionals trying to deal with the vapor intrusion problem. I'll introduce various statistical analysis and modeling tools that we use to understand better what is behind these transients and offer some insights into what this implies regarding site investigation techniques. Now, I suspect that most of the listeners today are familiar with vapor intrusion, but for those who are not familiar with it, Vapor intrusion is not a uniquely U.S. problem, and it certainly isn't confined to Department of Defense site. It involves vaporization of volatile organic chemicals that have been leaked, spilled, or were dumped on the ground, and that these vapors travel through the vadose zone, entering structures built atop the contamination. Like radon, the concern with vapor intrusion is long-term, low-level exposure to these chemicals. Low concentrations do matter, and one of the questions that has to be asked is, what is the right way to characterize the concentrations of concern in vapor intrusion? In terms of benefits to the Department of Defense, vapor intrusion assessment has historically been very empirical. Measuring concentrations of contaminant vapors at impacted sites, of course, makes sense. But the field results have often been very hard to interpret. And one big problem is that some very careful long-term studies have shown large variability in indoor air contaminant concentrations that have been difficult to explain. These kinds of temporal variations in indoor air concentrations at impacted sites make it very hard for regulators to deal with the problem. What exactly is the relevant exposure? The point that I'm going to explore here today is that mathematical modeling tools can help shed more light on the problem of transients in vapor intrusion and give better insights into how they can be managed. I'm going to turn now to the three well-known, well-studied vapor intrusion sites. The one on the left is the Arizona State University house outside of Hill Air Force Base in Utah. And the middle picture is of EPA's Indianapolis Vapor Intrusion Experimental House. And the picture on the right is of Naval Air Station North Island in California. All three of these sites have been the subject of extensive publications and presentations. And what I'm showing here are snippets of data that illustrate the problem of transients in vapor intrusion. They all show that the levels of, in this case, chlorinated solvent contaminants can vary by orders of magnitude on the time scale of days. And of course, this makes managing the sites very difficult. Now, the question that came up as we began this work is, these very well studied sites, are they or are they not representative of a broader range of vapor intrusion sites? In other words, is this kind of transient to be expected or maybe say feared at all vapor intrusion sites? Empirically, the results from the field have suggested not, but modeling can help tell when it might occur. Now, we distill the vapor intrusion situation for purposes of modeling to a very simple picture. I'm going to focus first on this little diagram on the left-hand side of the slide, which shows a generic structure with a foundation built atop a contaminated site, showing the groundwater level at some depth beneath the foundation. The focus really in this kind of modeling work is what happens in the vadose zone that involves the transport of the contaminants from the groundwater into the foundation. And the details of that are shown on the larger figure to the right. And what this figure shows is really the essential elements that go into building a model. So once again, at the bottom, we have the groundwater source of contaminants that vaporize and make their way through the vadose zone into the house. We're showing the foundation of the house, showing generically cracks or breaches, which are the entry pathways for the contaminant. Now, in some cases, in the modeling work that we've done, we've added a gravel subbase between the soil and the foundation. as is common in much construction. And in some cases, we've added a preferential pathway that is a conduit that brings contaminated air, soil gas into that gravel subbase. So this is the basic picture that we'll be developing a mathematical model for. Now, what we do is we construct a model of how the contaminants can enter the structures. The structures themselves are very often depressurized relative to their surroundings, leading to an advective flow of soil gas into the foundation and the building. We model this part of the process using Darcy's law, shown here, and we superimpose upon the solution that we get for the soil gas flow the species transport equations that involve an advective carrying of the contaminants with soil gas, as well as their separate diffusional transport through the vadose zone. These allow us to calculate the entry rate of contaminant into the building, which allows us to calculate the indoor air concentration, or to predict the indoor air concentration, given that we know the air exchange rate, shown here as AE, the volume of the building of concern, and CK is the entry rate through the crack. We solved this package of equations using the finite element method. And this spider web diagram in the lower right is a typical mesh that's used for representing the vadose zone beneath the structure. The hole that one sees in the middle here represents where the foundation sits within the vadose zone. The finite element method is a very well developed method in engineering modeling. There are many commercial packages available for solving these kinds of equations. We happen to use an off-the-shelf package called COMSOL. Now, the results of a typical calculation are shown here in this particular slide. The question that we addressed in this calculation was, how much of a difference does the degree or extent of indoor depressurization influence what is observed in terms of indoor air concentration? I'm plotting indoor air concentration here in terms of the well-known attenuation factor, which is simply the ratio of the indoor air contaminant concentration relative to the groundwater source concentration. And the x-axis shows the indoor-outdoor pressure difference, where the negative values indicate depressurization relative to ambient, and positive values overpressurization of the structure relative to ambient. Now, the left figure shows that for a situation that is akin to what exists at the Arizona State University site, if there's no preferential pathway bringing contaminants to the gravel subbase, the pressure fluctuations that will normally take place in the house really don't lead to large measurable transients. In other words, we're seeing here on a log scale that it's practically a flat line, so independent of the applied indoor pressure. On the other hand, on the right-hand figure, we see that with the existence of a preferential pathway that enters the gravel subbase, there is a very large effect of the degree to which depressurization of the structure takes place. And this is because of the enhancement of advective entry of soil gas into the structure, which brings with it the contaminant. So this is a typical kind of a modeling result that is available using the techniques that we discussed. And it points to the fact that the preferential pathway is a critical element in determining the very large transients that were observed at the Arizona State University house, where a land drain served the purpose of being a preferential pathway into the structure. Now, mathematical modeling also warns of other kinds of issues that will come up in characterizing vapor intrusion. Quite often, it's the case that the potential for vapor intrusion is determined by looking at groundwater contaminant concentrations and using those with Henry's law to estimate a source vapor concentration. One needs to be careful in doing that, and this figure illustrates why. What I'm showing here, in particular in the right-hand figure, is the concentration that is observed at a particular depth or height, I should say, above the groundwater source, given the existence of a capillary fringe. These calculations happen to be for a sandy soil, and the dimensions here are in meters. So over the course of about 20 centimeters of capillary fringe, the source concentration is reduced by about 2 orders of magnitude, depending upon the particular assumptions that one makes in the model. So this warns that one has to be very careful in characterizing the source strength. Where exactly are you saying that you know the vapor source concentration? Another aspect that models are very good at exploring is shown here in these color concentration profiles. The surrounding soils around a structure make a very large difference in what is observed. Now, what I'm showing in the upper left here in this pair of panels is a sandy clay soil with a structure. Again, the cutout is showing where the foundation of the building exists. And there's a gravel subbase that's barely visible in this diagram right underneath that foundation. The colors indicate the concentration levels of contaminant, with blue being relatively clean air and red being high concentration of contaminant. The point that I'm making in this slide is, first, if you compare the results for the sandy clay soil with those for sandy soil, no clay, you can see there are vast differences in the predicted concentration profiles in the soil beneath the building and indeed around the building as well. So the soil is predicted to make a very large difference in terms of the ability to transport the contaminant from the groundwater source into the structure. The other thing that is shown in this figure is that if you look at the lower panels for the sandy clay and the sandy soil, this shows the impact of having a preferential pathway entering the gravel subbase. And again, one can see there's a very large difference in the profiles that are created when one has this kind of a preferential pathway feeding contaminant directly to the subbase of the house. You can also see that with a preferential pathway present in sandy clay, the indoor air concentration, contaminant concentration, is increased by 3 orders of magnitude, as compared to in the case of sandy soil, where it increases by only 1 order of magnitude. So this shows the very important interplay of preferential pathways with the structure of the soil and subbase beneath the structure. Now, just how good are the models in actually predicting real field data? I'm going to return now momentarily to the Arizona State University case. What we've modeled here in this figure is something that is somewhat like the Arizona State University house in size and the gravel sublayer feature and the preferential pathway feeding it. We haven't tried to capture all of the details for the purposes of this illustration. But what I'm showing here is, as a function of the extent of depressurization or overpressurization of the structure, what is happening to the indoor air concentration. Alpha GW again refers to this attenuation coefficient that I described before, the indoor air concentration relative to source concentration. And you can see that we are doing a reasonable job of predicting what is going on at the Arizona State site, where these points represent actual field data from the Arizona State site. So again, we weren't trying to do a very detailed model of the ASU house, but we have basically the right size and the right kind of geometry for it. And this is also emphasizing another point, that is the importance of the gravel sublayer. We have here the orange line showing what we predict if there weren't a gravel sublayer. Clay soil is not very permeable, and so it doesn't allow nearly the kind of advective entry opportunity for contaminants as exists with a gravel subbase that is fed by a preferential pathway, here indicated as PP. Now, at Arizona State, they, upon discovery of the preferential pathway, closed it at one point and then performed similar sorts of indoor air concentration measurements. And you can see here are the data from that period of time, much, much less variation with time and with the applied pressure in the case of the preferential pathway having been closed. So the model does a good job of predicting this kind of behavior at real sites. Now, I'd like to look at another kind of site to leave a correct impression that it's not only preferential pathways that can lead to large observed variability. Here, what I'm looking at is some data from Naval Air Station North Island. And this is not modeling, but a statistical analysis of the time series data. What we're looking at here is measured indoor air concentrations relative to the time series mean for the site, again, as a function of the degree of depressurization or overpressurization of the structure. One thing that is very obvious in this figure is that as the extent of depressurization increased, the excursions in the direction of higher concentrations greatly increased. In fact, you can see that there's a very clear correlation with pressure as to what is observed indoors at North Island. North Island is a very different kind of a site in that it didn't have a preferential pathway. The Arizona State University results plotted in the same statistical way are shown here, emphasizing the fact that most of the ASU results were from a much, much smaller range of internal to exterior pressures. In other words, the pressure fluctuations at ASU were much smaller than at Naval Air Station North Island. And so the explanation here for the big variability in concentrations observed with time at North Island is that the pressure driving force is a much more significant factor at North Island than it is at the ASU house. So the modeling is indicating that there are different kinds of factors that can drive the very large variability that is observed at different kinds of sites. And what this says is that it's very important to correctly obtain the data that are key to prediction of indoor air concentrations. And those key data are those having to do with the subsurface geology, those things that determine advection and the steepness of subsurface contaminant concentration gradients. During the site investigation, you need to capture these kinds of details that determine these factors. Now, the ASU house, as I indicated when I showed the slide a moment ago, really exhibits, relative to North Island, a very small pressure driving force, but as you can see from this slide, still a very significant degree of variation in observed indoor air concentrations. Now, the orange bar is for the preferential pathway open. We've already talked about why that has a big impact. But if we look at the green blob of data, if you want to call it that, we still see that an order of magnitude fluctuation is not uncommon at these kinds of sites, even when there is no preferential pathway operating. So what's going on there? What we looked at was the fact that there is actually quite a bit of variation of the air exchange rate together with the variation of indoor-outdoor pressure difference, and that it has seasonality associated with it. If we looked at the data from the ASU House, the time series data, we saw that the winter season was actually characterized by a higher degree of negative indoor pressure and a higher degree of air exchange than the summer season, which tended to be very nearly pressure neutral or even slightly positive pressure and characterized by a much lower air exchange rate. What this does is it imposes on top of a pressure driving force other factors that determine the variability that one will see. And this is the figure I showed before, showing our predictions for the ASU House. Now, I'll say that the vast majority of data from the ASU House were taken in this range between plus and minus 2 pascals. What I'm showing here as this blue band around the center line is the effect of these kinds of natural variations in air exchange and pressure fluctuation. So in other words, an order of magnitude kind of variation in predicted indoor air contaminant concentration comes out of this analysis naturally when you take into account both of these factors. We, in fact, even looked at the influence of air exchange rate fluctuations on a 24-hour basis for this site. Again, there's a lot of data here, but let me just say that on a 24-hour basis, when the preferential pathway is open, this lower left-hand figure shows that we get almost an order of magnitude fluctuation in the concentrations, whereas when the preferential pathway is closed, there's about just less than a factor of 2 variation observed over a period of 24 hours. And this brings us to the implications for sampling of indoor air, in that if one goes in and samples over the course of one day, one shouldn't be expecting to see much more than about a factor of 2 variation in terms of minimum to maximum indoor air concentration. However, if one looks over the course of 3 to 6 months, a much larger degree of variation emerges because of the seasonality and the impacts on the pressure and air exchange rate. And of course, with the preferential pathway open, an even larger, several 3 orders of magnitude variation can be expected if one is sampling in different seasons. So the implications for sampling indoor air are that a one-day sampling interval is likely to result in less than a 2 to 3 factor difference, and differences in order of magnitude are typically detected only at longer times. And I'm just about finished with my discussion, just showing here that the non-uniformity of the vapor intrusion process in a temporal scale is also predictable using modeling, and it implies the fact that there can be a problem in terms of doing subslab sampling. What time do you actually take a sample in order to determine what the subslab concentration might be? The final point I'm going to close with is looking at the modeling of controlled pressure method as a characterization tool for vapor intrusion. There's a limited zone from which contaminant can be drawn in a scenario where the house is deliberately depressurized to create a worst possible case scenario for vapor intrusion. This is a commonly used technique. We've modeled it, and again, I'm not going to focus on the details of that equation. I'm out of time. But the warning from this modeling is that, let's focus on the right-hand figure here. The normalized indoor air concentration, by virtue of the fact that one is looking at a transient in the subsurface in addition to in the house, is that it is going to give you very different kinds of results in terms of indoor air concentration, depending upon when you begin to do the sampling, how many hours after the controlled pressure method is initiated. And again, modeling very nicely predicts this. So let me then close to say that I hope I've given a little bit of a flavor that models of vapor intrusion can help identify non-obvious results that come from the interplay of a lot of different factors in vapor intrusion. Order of magnitude transients are the result of unusual circumstances, preferential pathways, or highly advective driving forces. They are not expected at most what you might call ordinary vapor intrusion sites. And the modeling can help define effective field sampling strategies in terms of defining how often one takes samples. And it's this combination of statistical analysis with modeling that is a powerful tool for understanding the real field results. So with that, I apologize for running over a bit, but I'll be happy to take some questions.
Thank you, Eric, for a great presentation. And as a reminder to our audience, you may submit questions by using the Q&A box on your screen. We have received a number of questions on the first portion of the presentation that Eric will answer. Eric, is there a possibility that temporal variations in measured indoor concentrations are linked to variations in groundwater contaminant sources?
Yeah, this raises the important issue of relevant timescale. Typical groundwater flow rates are, of course, measured in meters per day, which means that with the large contaminant plumes typically involved in vapor intrusion, it's unlikely that a source is going to move from or to a site very quickly. But more importantly, if you use a typical soil vapor contaminant diffusivity value of about 10 to the minus 6 square meters per second, and you have a source that's, say, 3 meters below the foundation, the time scale for change that's going on in the source to be felt at the foundation is of order the distance to the source squared divided by diffusivity, or in this case, about 9 million seconds or about 100 days, roughly speaking. So this means that transients driven by changes in the source are very, very slow compared to what's been measured at the sites I was talking about.
Great, thank you, Eric. Another question is related to cost. You mentioned that mathematical modeling tools are relatively inexpensive. What do you exactly mean by that? Are they inexpensive relative to other tools that are available, or and can you try and put a dollar figure on what it would take to develop such a model for one site?
Sure. Well, relative, when I say relatively inexpensive, I'm saying that they are relatively inexpensive compared to other site investigation tools. That this kind of mathematical modeling would add relatively little to the expense of characterizing a site. The modeling work that I showed here today involves a desktop computer and a commercial solver package that together cost only a few $1,000s. And so the expense of actually setting up the hardware and software to do this is very inexpensive. The time of the person who does the modeling, of course, is going to cost something. But I'll point out that most organizations that are going to be interested in vapor intrusion probably already have somebody who's doing this kind of modeling for some other purposes. And so these finite element solvers are now pretty much turnkey already, and there wouldn't be a very steep learning curve, I'm sure, for somebody who is used to doing other kinds of modeling to come up to speed.
Great, thank you. One of our audience members is asking whether you can recommend an open access model for modeling the BVI pathway.
Okay, well, let me say there are a couple of things. One is we are happy to give away our technique, our modeling technique. We don't have anything that's proprietary. We're happy to show anyone how to use solvers like the COMSOL solver to work on vapor intrusion problems. In fact, I believe CERTA BSTCP is going to probably be arranging another workshop for training people how to use it. Stay tuned for that. There is also on the web, I think the website is pvitools.com, a spreadsheet tool developed by one of my former PhD students called CVI2D and PVI2D that is a simplified version of the kinds of models I was talking about here. It's a two-dimensional spreadsheet tool that is akin to what formerly was the Johnson and Ettinger tool on the EPA site, but it is a two-dimensional tool, so it does take into account the fact that lateral processes are also important in characterizing the vapor intrusion situation.
Great, thank you. And one last question before we transition to Todd, and it's from one of our Canadian colleagues. Is modeling based on full concentrations accurate for determining attenuation coefficient?
I'm sorry, I missed the very first part of it. Is modeling on what kind of conditions?
Based on soil concentration.
Soil concentration.
Is it accurate for determining or calculating attenuation coefficient?
Well, again, I think we've shown that we can successfully predict the kinds of variations that are seen at these well-characterized sites. And so it depends on what kind of accuracy one is looking for. You know, certainly it would be foolish to try to expect 1% accuracy or anything of the kind. I think certainly correct order of magnitude is expected, and better than that to a factor of 2 or 3 is, depending upon the quality of the inputs, certainly possible.
Great, thank you so much, Eric. We still have a few questions remaining for you, and we'll get to them at the end of the webinar during the final Q&A, but it is now time to transition to our second presentation on today's webinar, which will be delivered by Dr. Todd McAlery, who is the practice leader for vapor intrusion services at Geosyntac in Toronto, Ontario. Todd has over 30 years of international consulting experience, focused mostly on chlorinated solvents and vapor intrusion. He has served as a member of EPA's expert panel on VI and authored or co-authored over a dozen guidance documents on the topic. Todd is licensed as a professional geologist in North Carolina and as a professional engineer in Ontario and British Columbia. He is an adjunct professor at the University of Toronto. Todd, please proceed.
Thanks, Rila, and thank you all for attending. I'd also like to thank Bill Wirtz and Darius Malley, two of my colleagues who did a lot of work on this project. Our main goal was to evaluate new technologies for optimizing mitigation systems with the goal of reducing the costs. The agenda for today's session will include several topics. I'm not going to focus too much on data. There is a final report already posted on the ES2CP website that includes a lot of data, far more than I could cover in today's talk. But I will try to go over our approach, how the data is collected, how it's analyzed, and some of the side benefits that come from that. For example, the building-specific attenuation factor is something we have now, a mathematical model to calculate. I'm mentioning that in response to one of the questions that was asked a moment ago. And that spreadsheet is something that will be posted to the ES2CP website, so it will be available for free. So without further ado, I'll carry on to try to give a framework for why we're doing this research. In conducting mitigation at a number of sites, we came to the realization that some of the radon mitigation contractors that we were subcontracting to help get the work done cost effectively had different approaches than what we had previously experienced in soil vapor extraction and other technologies that were pretty close to one another, but the approaches were quite different, which got us to thinking about, why exactly is that? In soil vapor extraction, one of the most common methods for evaluating the radius of influence of an extraction well is to collect data measured static vacuum at different radial distances, plot that up on a semi-logarithmic plot of linear vacuum versus logarithmic distance. You don't normally get 20 or 30 data points like shown on this plot, but this is research, so we got more data. Usually you're making measurements with 2 or 3 different radial distances, and depending on which distances you get, you might have a different estimate of the slope of the line of vacuum versus distance. That would give you two different estimates of the radius of influence. It could be quite significantly different. This was not very satisfactory to us, so we thought, well, let's see if we can get into this in a bit better detail. Then with the conventional design, you also are comparing to some target vacuum. And usually these are specified in guidance documents, but the more we made measurements across the floor slab of real buildings, the more we saw that they weren't the same from building to building. In many cases, it's almost a unique signature, unless it's a flat line. There are, some buildings that are so leaky that they can never really generate positive or negative pressure, no matter how much air you move in or out of them. But for most buildings, especially ones with ventilation systems that either extract air or blow air into the building, you'll see some kind of an effect of that that's either balanced or not balanced. It might be static or cyclic. And getting to understand this is actually quite important because, as Eric mentioned earlier, this is an important driving force. Regulatory guidance documents might not say you have to measure this, but I'm saying it, you have to measure this. This is an important parameter. So our conceptualization is that we've got a 2-layer system. There's a concrete floor slab over top of either native soil or compacted granular fill material. Most building codes now specify that fill material should be placed below floor slabs, so more recent construction tends to have a gravel layer or granular fill layer. But older construction sometimes doesn't. But most often there's something more permeable below the slab than concrete. So in this conceptualization, we've got a conductivity and a thickness for each of the 2 layers. K is conductivity and B is thickness. Flow is going to be mostly horizontal through the layer below the slab, and then there's some vertical downward flow across the slab. That's the whole goal of these systems, is to prevent upward flow by creating downward flow. Now, this conceptualization is really no different than the Hentisch-Jacob-Leakey aquifer model of 1955, which was designed for groundwater assessment, where you have an aquifer that has a pumping well screened in it and you're extracting water from that well. The drawdown cone extends outwards until the amount of water leaking downward through a leaky aquitard equals the amount of water being extracted, and then your drawdown cone stabilizes and it doesn't spread out any further. So in our view, this is 2 different fluids, air and water, but otherwise both looking at a 2-layer system, where the lower system is the more permeable one, the upper system is the less permeable one. Horizontal flow occurs in the deeper one, and downward flow occurs across the shallower one. So with that conceptualization, there are 2 key parameters: the transmissivity of the material below the floor, which is just the gas conductivity times the thickness. And then this parameter that Hentisch and Jacob defined as leakins, which is just a combination of parameters that ends up simplifying later equations, but it basically relates to the vertical permeability of the floor slab. So how, the horizontal permeability of the stuff below and the vertical permeability above are the 2 main factors here. With those two parameters, you can plug them into a series of equations that give you a lot of useful information. For example, you can look at vacuum as a function of distance, velocity as a function of distance, travel time as a function of distance, the proportion of flow originating below the floor versus originating from leakage through above as a function of radial distance. And we also recently derived, so all of those four were available from Henderson, but we recently also derived an equation for the building-specific attenuation factor. So basically, do a pump test, measure the T and B, and you get all this useful information. That's a pretty fun thing to have. Our scope of work included 4 buildings of different sizes and dimensions, orientations. Building 200 at the Raritan Arsenal, single story, a couple thousand square foot, more or less like a bungalow. Vandenberg Air Force Base, building 11193, 4 dry cleaners, so we have a stout tetrachloroethylene source beneath the building, single story slab on grade, not heavily insulated, fairly leaky building. Cindoor Manor, which was described earlier in Eric's talk, near Hill Air Force Base, extensively studied by Arizona State University, and another building at Raritan that was much larger, so a big commercial style building. And our methods are not much different than a salt vapor extraction pilot test. We've got a fan. Usually it's simpler and cheaper and less expensive to purchase a shop vac for a particular project and give it away to somebody at the end than it is even to ship a decent sized blower back and forth to a site. So we often use a shop vac as a driver. It goes to a suction point below the ground through a straight piece of tubing that gives us essentially as close as we can to laminar flow that we can measure velocity in. We've got sample ports for measuring vacuum and collecting Lundbach samples for field screening parameters, PID, landfill gas meter, and a connection for SUMA canister sampling with a discharge pipe that takes us to the source. The tests usually run for anywhere from 15 minutes to an hour. During that time, we collect data of a number of different types. Vacuum can be measured over time using a logger, digital microphonometer. And you can do that both in the time before you start applying suction to get the baseline fluctuations, but you can also make measurements over time after you start suction. Usually things stabilize pretty quickly, and then when you turn the fan off, the vacuum dissipates fairly quickly. But the analysis of that transient drawdown and recovery data is similar to a groundwater pumping test, and that data can be analyzed independently of the vacuum versus distance data. So we put probes at different radial distances so that we can measure the profile of vacuum versus distance as well. Vacuum versus time and vacuum versus distance are 2 independent data sets, but they're both useful because they both relate back to the leakance and transmissivity parameters. We measure velocity using helium. You can do helium tracer testing in 2 different ways. You can put a little pulse of helium into a probe. It'll migrate towards your suction point, and you can monitor the arrival at the suction point with a helium meter. The helium meter is like $100 a day rental, and helium, you can get even party supply store helium. It doesn't need to be ultra pure. And just a balloons full of helium is usually enough to do this kind of test. Another type of helium test is to reverse the fan and blow air into the subsurface, adding some helium to that at a small percentage, and then watching as it migrates underneath and arrives at the various probes at different distances. We're also collecting samples from the vent pipe and measuring the velocity in the vent pipe so that we can get a measurement of the mass per unit time that's being extracted. Most of these lines of evidence take very little time to implement in the field, and once you're in the field anyway, don't add very much to the cost. So they're quick and easy and pretty painless to implement, not expensive or time consuming, and so they provide a lot of extra useful information. Looking at the vacuum versus time data, this is a plot straight out of Actisolve, which people have been using for groundwater pump test analysis for years. You just need to do a correction to express your gas pressure in feet of air head, and then you can import it into Actisolve and fit to the Hentrich-Jacob model. In this case, what we're showing here is a blue line that is the mathematical model, and these little squares are the measured data points. And if you look how closely those 2 match, it's pretty encouraging. They would not match well if the real world conditions were very different from the model assumptions. The fact that they do match so well is quite encouraging. We've done hundreds of these tests, and we've found this kind of a fit is common, like 95 to 98% of the time you'll get an amazing fit like this, which is quite encouraging. The times when you don't get a fit like this are when your response is so fast that even the data logger can't keep up, or the rate at which it takes the fan to spin up to speed is slow relative to the assumption of an instantaneous start, or where there's preferential pathways below the building floor. So this analysis is one way to get a hint at preferential pathways. The tracer test data looks either like one of these two plots. The interwell test is a slug, so the concentrations will reach a peak and then dissipate. The time from the middle of the injection to the peak is the travel time. So in this case, you can see 25 seconds from a radius of 12 feet. That's 25 seconds of time, and time is money. It's not expensive. On the right is the result for helium flood, and because the helium is added continuously as opposed to just a slug of helium, the concentration starts off at a low level, goes up to a level and stabilizes at whatever level you're injecting it at. And the arrival time is the time it takes to get halfway there. So in this case, for these two, about 45 and about 60 seconds. Again, not time consuming and therefore not expensive. So this data can be entered into a spreadsheet model that I mentioned earlier. In this case, we have radial distance and vacuum that populate the two charts in the upper right. In one case, this is linear vacuum versus logarithmic distance. In the other case, it's logarithmic vacuum versus linear distance. But these two plots are both vacuum, static vacuum versus distance. The reason we've got both of these plots is that you get better resolution and the ability to fit both the near end and the far end data. By simply adjusting transmissivity and leakance parameters after putting in the flow rate at which these measurements were made. If you measure velocity with or travel time with a tracer test, you can also enter that data into the spreadsheet, which will populate this curve. And then you can adjust the thickness of the zone of active flow and its porosity in order to match these data points up as well. Once the model's been calibrated to vacuum versus distance and the travel velocity, then you can rely on those transmissivity and leakance values to provide predictions of the velocity and the downward flow. And in each case, you can establish target values that you might consider to be appropriate for your mitigation system. So that's vacuum versus distance, that's travel time, that's velocity, and that's the proportion of flow across the floor. And in each case where the model line crosses that target, you could pick off a radius of influence of, say, 60 feet, of 45 feet, of greater than 70 feet, and around 50 or 60 feet. And this gives you a much more informed view of what the radius of influence is for your particular system. With this kind of an approach, we developed optimal designs for, I'm just going to show you two of the four buildings. In building 11193, a conventional radius of influence of somewhere around 19 feet would have resulted in 11 suction points, but we were able to demonstrate that one suction point at only 25 CFM was adequate to achieve protective indoor air quality and good mass removal rates. So the result is a lower capital cost, a lower operation and maintenance cost. The total net present value estimates, different by almost a couple $100,000 with an incremental cost of only about $10,000. So the cost effectiveness of this technology, I think is pretty clearly demonstrated. And just to show another building, at building 205, a system had previously been installed with an assumed radius of influence of about 28 feet, resulting in 27 suction points. We were able to demonstrate that only 2 suction points were required. And again, there would be savings of about 10 times the cost, the incremental cost. So very cost effective in terms of its implementation. I mentioned earlier that we developed a calculation for the building specific attenuation factor. Again, it depends on the transmissivity and the leakance. So once you do the pump test and calibrate the model, then you get these two parameters. The delta P is that differential pressure across the floor slab, which can be measured with the data logger, and that's a relatively affordable piece of equipment, and it does all the work. The height of the building you can simply measure, and the air exchange rate is something you could either take from the literature, or if you have an incentive in doing something more detailed, you could do a tracer test to work out the air exchange rate. You could also get the air exchange rate from a blower door test, which I'll talk about in a minute. We didn't have empirical attenuation factors at Raritan 205 because the indoor air concentrations were really not measurable. And at Sun Devil Manor, it's hard to come up with one attenuation factor because there's a pretty broad range of concentrations measured there. But for the other two, buildings are calculated attenuation factors matched up, within one significant digit of those measured by measuring subslab and indoor air concentration data. So this is commemorated in an EST article if you want more details on that. That attenuation factor can be used to develop building-specific subslab screening levels. This is particularly interesting for the DoD because many of their buildings are designed in such a way that they're not going to have very high attenuation factors that would result in very low screening levels. And so you could potentially have buildings where there was a release off in one area and you don't need to mitigate the whole building or down to very low screening levels in order to achieve protectiveness. And then you might end up just having a target treatment area instead. And that could result in more affordable and more practical and easily implementable mitigation systems. I want to talk a little bit about mass loading. Vapor intrusion occurs usually because there's some flux upwards from the subsurface towards the building, often characterized by a one-dimensional diffusion equation. But you can measure that flux in a couple of different ways. You can extract gas from below the building, and the flow rate that you're extracting at times the concentration that you're pulling out gives you a mass per unit time. And you can also depressurize the building, and the flow rate coming out of the building times the indoor air concentration also gives you a mass per unit time. So you have two different ways of measuring the mass per unit time that's coming up towards the building. And, to make a long story short, when we did that kind of testing, we got these kinds of results. You can also calculate a threshold value that would be required to sustain indoor air concentrations at a concentration of concern. For example, the big building like building 205 at Raritan would require a few grams per day of trichloroethylene to pose a concern. And no matter how hard we sucked on the building or from below the building, we couldn't get anywhere near that much mass. This provides you with a line of evidence to argue that a system probably isn't even needed. We continue to operate a system in the abundance of caution, and also possibly because the tenant of the building currently is the United States Environmental Protection Agency. And, we'd want to make sure that we're protective for them. The other buildings showed mass removal rates that were much higher than the threshold mass, which means the system is justified. And the amount that we're removing from the subslab system was generally higher than the amount that we could get by, exerting a vacuum on the building, indicating that our systems are extracting as much or more mass than they need to. And that's something that helps you assert that they are protective. And another independent line of evidence that adds to the flow and vacuums type measurements that we had previously. Another interesting side benefit of this technology is the ability to identify the presence and possibly location of preferential pathways, which up until this point has been elusive. If you measure vacuum as a function of distance and it matches right up with the model, then the two-layer system, is reasonable to assume, applies at the particular site. Where there's a preferential pathway, air will flow into the subsurface more easily, and where air flows more easily, vacuum dissipates more easily. So where you see vacuum that's lower than the rest of the trend, that gives you a hint, and that hint should not be ignored. There has to be some form of flow towards that. Now, that could be either a floor crack that's providing flow from indoor air, or it could be a subsurface drain that's providing air from a lateral distance, like the land drain at Southern Devil Manor. This doesn't distinguish between the two, but it does at least give you a hint that there's something to look for. And we noticed also that there are times when you might have a low vacuum level at a certain spot, but even further away have a greater level of vacuum. So these effects may be somewhat localized. And how localized they are may relate back to whether it's a leak across the floor or whether it's a subsurface pipe. Perhaps a leak across the floor has a more localized effect than a subsurface pipe. This is still early days, and we'll learn more about that as time progresses. So we want to just try to wrap up by saying that mitigation primarily in the past. Static vacuum and indoor air sampling have been the two primary mechanisms for evaluating and designing systems. But now looking at the baseline differential pressure, static vacuum in the near field as well as the far field helps us calibrate those plots a little better. Doing the transient vacuum testing is really just a matter of turning the fan off, letting the vacuum dissipate, turning it back on, letting it reestablish. Usually that takes only a few minutes, but it gives you another line of evidence. The helium tracer testing is either blow a puff of helium into a probe near the extraction point or reverse the fan and blow helium into the extraction point. Either of those tests can also be pretty quick and not that challenging in terms of their implementation. Then pop the data into a spreadsheet model. It's pretty quick, it's pretty easy, it's pretty user-friendly, and you can get a much better sense of what your radius of influence would be, particularly for those buildings where you have a large enough one to require multiple suction points. You could even use it to select a fan by adjusting the Q value down to whatever level is sufficient if all you need is a single suction point. And then vent pipe sampling just to get the mass removal rate. Again, that's just hook up a sumi canister and collect a sample. Or if you wanted a longer term average, you could drop a passive sample in there, as long as it's got a windscreen, because the velocity in there is going to be pretty high. And then optionally, you could also do the building pressure cycling to establish a baseline mass removal rate. You could look at differential pressure in the long term over time. And or even systems now where you can have the fan speed tied to the differential pressure monitoring to make sure that you suck harder when you need to and not when you don't, to minimize the amount of energy draw. And now that we have a line of evidence that can lead towards closure, you know, we might want to proceed with rebound and testing and closure applications as appropriate for a particular site. I've just divided these into two different categories of recommended and optional, just because the recommended ones don't really add much to your cost, and they're probably worth doing almost all the time. The optional ones add a bit more to the cost and may or may not be justified, kind of depending on a site-specific or case-by-case basis. So in conclusion, I'd just like to say we believe that the two-layer model does a pretty good job of matching field data. Where it does, it gives you confidence that you're actually looking at a system that more or less matches the model assumptions, and where it doesn't, it gives you hints of preferential pathways, which in itself is useful. It gives you a little more confidence in your estimates of radius of influence because you'll be able to look at it from different lines of evidence. And I'm not sure whether these are side benefits or just benefits. You may end up with fewer suction points, lower extraction rates, both of which will lower your costs. The mass loading gives you a potential exit strategy where it's appropriate. Having indications of where and whether you might have preferential pathways is useful, and having a building-specific attenuation factor is also useful, particularly for those buildings that are not very susceptible to vapor intrusion, and you have low-level concentrations below them that are above generic screening levels, but not high enough to really pose a problem. So the benefits to the Department of Defense are pretty similar to those I just listed. The DoD has a lot of buildings, and you know, the total amount of costs that might be incurred in invoking mitigation at all of them could really add up. But if you can do a small amount of testing to save a lot of money, then there's potentially a lot of money to be saved. And this provides additional confidence and the other things that I just mentioned. This is implemented through a user-friendly spreadsheet model, so it should be pretty easy for people to pick up. I do encourage people that are interested to go to the website and look up under ESTCP ER 2013-22. If you just search under that, it pops to the site. And a screening or a bar on the right-hand side allows you to download the final report. All the detailed data is in there. There's far too much to be able to cover in this webinar. And if you have any questions, technology transfer is part of our mandate, and I'm happy to take a call either to my email address or to my cell phone number. And with that, I'd just like to thank you all very much for your attention.
Great, thank you so much, Todd. We have a number of questions that came through for you. Starting with, how do you know when you have enough communication test points?
Oh, that's a good question. It's always a good idea to do a building reconnaissance and visual inspection. Where the floor is bare, you should pay particular attention to expansion joints, utility penetrations, and other discontinuities in the floor. You should take care to look at whether or not the floor is covered with epoxy or not, what kind of condition it's in, whether you see any stress fractures, etc. DoD buildings tend to have pretty robust floor slabs in my experience, and so and in many of the buildings they're exposed. So taking the time to do this survey is usually well worthwhile. Expansion joints tend to be sealed with caulking. Caulking doesn't always last the way it's supposed to, and so if you see obvious examples of caulking that's in poor shape, then you might want to consider the location of your communication test points to assess whether or not those are leaking. If you put one near the expansion joint and one, further from the suction point, then that gives you the ability to test the amount of leakage at that point, as I mentioned from one of the plots earlier. We always like to have at least one communication test point that's pretty close to the suction point, because if you try to measure the suction at the wellhead, there's not only the suction from frictional resistance through the soil, but also turbulent losses from increasing velocity as you get closer. And so that tends to be biased high, and I'd recommend not using it. To put another probe in 3 feet away from your point of suction doesn't take much time or money. And it provides you with a measurement of near field velocity or vacuum that is much more reliable for the model calibration.
Great, thank you, Todd. This is a question from the California Department of Toxic Substances Control. Can you speak to the long-term indoor air monitoring needs with regards to frequency and duration to ensure the efficacy of mitigation systems?
That's a good question. I think the answer is it depends. If you have a system that is removing a very high rate of mass removal, much higher than the threshold mass that could potentially pose a problem, and that happens in some cases. You might have enough to justify a soil vapor extraction system, then I would recommend monitoring on a more frequent basis. And there's several reasons for that. One is the discharge of the vent to the atmosphere is intended usually to be carried away by the wind, which averages around 9 miles an hour nationwide, but it's not always windy. And so there are times when the exhaust can recycle back into the building, particularly if there are building mounted air handling units that are sucking in large amounts of air and blowing it back into the building. There's probably more justification for doing indoor air sampling where there are sensitive receptors. There may be more justification where there are compounds with acute effects. Where the compounds present are only ones with chronic effects, I would recommend long-term sampling as opposed to short-term. So we typically collect samples with summit canisters over 8 to 24 hours. In previous research, we've looked at passive samplers with sample durations that are, a couple weeks to a couple months. And for carcinogens, the long-term average concentration is actually a better surrogate for the risk calculations. So there are several considerations. Also, the size of the building might reflect on the number of sample locations. If it's just a single family residence at one location may be sufficient. If it's a very large building, the one in each air zone might be considered. So it's hard to give one single simple answer to the question.
Great, thank you so much, Todd. Another question, can you comment on the regulatory acceptance of designs based on the recommended diagnostic additions that you talked about?
Well, it's pretty early days yet. What we found is regulatory acceptance usually depends on their understanding. If they've got time to sit with you and go through the data, the analysis that I showed today isn't rocket science, and it's not black box. It's kind of on the table, and it's pretty clear. I mean, when you measure vacuum, you measure a vacuum. It's the static vacuums at least tend to have very little variability, and then once the system is up and running at a steady flow rate. So the analysis is not that challenging. It kind of depends on whether the regulator has some familiarity with mathematical analysis of fluid flow through porous media. If they're hydrogeologists, they'll usually get it pretty quickly. And if not, then they may have a resource person within their department that they can call on to help with the analysis.
Great, thank you. Are there any other lines of evidence for assessing the leakage of floor slabs other than the ones that you described?
Yes, I didn't get into it, but we often bring a landfill gas meter out with us and measure oxygen and CO2. Soil gas tends to have a little bit of CO2 and a little bit of depleted oxygen because of aerobic microorganisms degrading organic matter in the soil and consuming oxygen and producing CO2 in the process. So if you're conducting a test like this and you monitor the concentrations of O2 and CO2 over time and they don't change, that gives you an idea that the floor slab is not very leaky. If they change in such a way that the oxygen goes up towards atmospheric levels and the CO2 goes down towards atmospheric levels, then it's likely that there's some leakage across the floor slab. And you can look at the rate of change with some mass balance calculations to determine the amount of leakage across the floor.
Great, thank you, Todd. And one more question before we pull Eric back in. How important is diffusion of vapors through the matrix of the concrete?
Yeah, that's another good question. The subslab venting systems that are designed only to achieve a certain level of vacuum, and then, as long as they've got the vacuum, you just assume everything's working fine, can be misleading. If you've got clay-rich soils, a vacuum doesn't necessarily mean much in the way of velocity. And so concentrations that may be quite high take a while to flush through. High concentrations can result in diffusion through the concrete at rates that are not negligible if your concentrations are high enough. And so once you get subslab concentrations up into the 1,000,000 micrograms per cubic meter range, which isn't very common, but it does happen, then I think you need to start worrying about diffusion through the concrete. And it might be that you would need to have a supplement to your subslab mitigation system. For example, indoor air purification through carbon filters, or perhaps increased ventilation rates for a period of time until the subslab concentrations start to diminish. They will eventually diminish.
All right, thank you very much, Todd. And then we're just gonna conclude here with some general questions, and we'll start with Eric. Eric, do you believe that we're at the point at which models can replace actual field work in characterizing a vapor intrusion impacted site?
I wish, but I think the honest answer is that at this point, it's fair to say that models should be looked at as one line of evidence regarding understanding of a particular site. The inherent complexity of unseen subsurface conditions and processes, again, represent the biggest limitation to more confident use of models. No model is really ever better than the inputs that are used to build it. At the same time, the models are still powerful in evaluating whether a particular site conceptual model makes sense, and along with that, whether a particular investigation strategy or remedy is appropriate. So again, bottom line, I think models at the moment still remain one line of evidence and not going to directly replace field studies.
Thank you. Todd, would you have anything to add on this?
Well, I'd actually just like to add one thing to what Eric said. If I'm driving from one place to another that I haven't driven before, I'll always go onto Google Maps and put in the two, points and have it tell me how long it's going to take to get there. It's basically doing a calculation to do that. And I don't take that number as gospel. I always post-process it and allow myself extra time for traffic or whatever. But I'm using a mathematical model even to drive from one point to the other. Why? Because it's available, it's quick, it's useful, and it's informative. And I would say the same thing for the models that Eric was talking about today, and even the spreadsheet model that we've developed here. It's quick, it's easy, it's useful, it's informative. Why not? It doesn't necessarily mean that you throw out the professional judgment. It doesn't mean that you're going to use that as your only line of evidence. If you're driving back and forth to some place, a lot of times you might say, oh, you know what, the traffic is worse than this really understands, or maybe it's overly conservative. And so your judgment will be informed over time and you'll get better at it. But the models are going to be helpful. Just incorporate them as part of your strategy.
Great, thank you very much. And what, in your opinion, is some of the decision logic for selecting between subslab depressurization, subslab ventilation, and soil vapor extraction as remedy options for vapor intrusion? Let's start with you, Todd, and keep it really brief, and then turn it over to Eric.
Good question. Yeah, if the vadose zone is thicker, then soil vapor extraction tends to have a larger radius of influence. If you've got more mass in the subsurface, then soil vapor extraction starts to have a benefit because you have more of a likelihood of actually getting to an endpoint someday. If the permeability below the floor is very high, then subslab ventilation might be enough, especially if the concentrations are not very high to begin with. If you knock the concentrations down, even if you don't have vacuum control, the occasional burp into the building won't carry any mass with it, and so ventilating might be all you need to do. And where the permeability is lower, then you might not be able to ventilate very rapidly, but you should be able to get a vacuum to propagate quite well.
Thank you, Todd. Eric, would you like to add to this?
Yes, I'd like to add a couple of things, but before I do, let me, if I may, correct one thing that I said before, and that is the website for getting the two-dimensional spreadsheet tool is pvitools.net. I think I gave the wrong address before, so that's pvitools.net, and that one is maintained by Dr. Yijun Yao and Jason Virginelli. So that's a very good site for getting a very easy to use tool. Another thing that I wanted to point out was many of the results that I showed have been presented in a paper that has just been accepted in Building and Environment. First author is Jonathan Ström. So if you're interested in more of the modeling details, they are available in that paper in Building and Environment. To go back to the question that you posed about SVE versus subslab depressurization, the one thing I can say is that the modeling tools that we're talking about lend themselves very well to evaluation of those strategies. In fact, we are doing those very kinds of calculations right now, looking at how many extraction points, with what kind of vacuum applied will be protective in certain kinds of scenarios. And so all I can say is stay tuned. We will soon be publishing some work using the same modeling tools to describe what happens in those scenarios.
Great, thank you, Eric. And maybe you can start us off with a response to this question from the California Department of Toxic Substances Control. For example, prior to constructing a building, how can modeling be used to predict vapor intrusion from data collected at empty lots, since the presence of a building can affect the subsurface soil gas equilibrium?
Yeah, that's a very important question, and in fact, my colleague Dr. Yao worries a lot about that situation. In fact, he points out that often in China, that is the question, rather than asking what's the impact on an existing structure, what is going to be the impact of putting a new structure on a brownfield. And so the answer is, of course, if one has the information about the source, that is source depth, source strength, and the soil, a model can offer much better insight than what would be available just by simply doing a soil gas survey, because as is well established, what happens when you put a building on a contaminated site is that you're putting effectively a diffusion block onto that site, and the contaminants will accumulate underneath that diffusion block. Now, the extent to which that is or isn't important depends on the footprint of the building, the lateral diffusion, extent of lateral diffusion, and of course, if one is concerned instead of with chlorinated solvents with petroleum, one has to take into account also the action of microbes in degrading the petroleum compounds. Is there enough oxygen in the soil underneath the footprint to take care of the upward diffusing species. So there are many factors that can be examined using a model, and in fact, I think that would be a very good way to assess what the impact of putting a building on an otherwise undeveloped parcel might be.
Thank you, Eric. Todd, do you have something to add?
Well, we have considered the possibility of putting a sheet down on the ground surface and conducting mass flux measurements. If you have, for example, a low permeability barrier and you're drawing gas from below it, whatever's migrating up towards it could be estimated as a mass entry rate into the building in the future. That protocol hasn't really been developed yet, so it would require a bit of work.
Great. Well, thank you both for taking all of these questions. And I'd like to remind everyone that our next webinar is on Thursday, July 25th, and it will focus on DoD-funded research on understanding underwater munitions mobility and behavior on the beach phase and in shallow, muddy environments. Registration is open, so please visit the SERDP and ESCCP webinar webpage to register for this and other future webinars. In fact, registration is open for webinars throughout the end of this year. Before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it at this time if you could please take a